Shall we start? Are you able to see the screen?
Yes, sir.
Okay. So, so let me just recall what is the what of this these topics up to now. Up to now, looked at Laplace equation. So the main thing is to find the fundamental solution and write the representation formula. Okay, basically we want to write u any function u of x belongs to Rn in terms of integral equation. Integral equation. Okay. It will involve the integral equation will involve integration over domain also, integration over the boundary also. Okay. Here is where we are using the Green's Green's identity. Here we are using the Green's identity. Okay. So, this is called the representation formula. Representation formula, that is writing u in terms of the fundamental solutions. What are the fundamental solutions? In R2, we found that log mod x is the fundamental solution. In R3, 1 upon mod x is the fundamental solution. And in general, in Rn, n for n greater than 3, r power, that is mod x to the power of 2 minus n. Okay, this is even 3. Basic radial functions. These are radial functions. Okay, these are radial functions. And what are fundamental solutions? Fundamental solutions are, as I mentioned before, that there is a constant here. Fundamental solution V of mod X or V of R is equal to, there is a constant involved, C1 plus C2 log mod X in case of n is equal to 2 and so on. C1 plus C2 upon mod X in the n is equal to 2 case, n is equal to 3 case, and this is equal to C1 plus C2 upon mod X to the power of n minus 2, n greater than 3. Okay, so fundamental solutions are those solutions where we can take the find the constants C2s. Okay, so anyway, this is C1s are there. Constants, addition of constant is also a solution that we can ignore these constants, but we have to find these C2s. That's what we have done before also. We have mentioned before also. C2, in each case, the C2 in 2 dimensions will be 1 upon 2 pi. Upon 2 pi and 1 upon 4 pi and so on. So these are the fundamental solutions with the constant. So now the representation formula will be always, in terms of fundamental solutions. Fundamental solutions are building blocks. Okay. So u of x in case of 2 dimensions will be some this log mod x should come into picture, and we'll have a log mod x will come into picture, and we will write exactly what is the that is basically these fundamental solutions. So there is an integral, yeah. Recall what is Green's identity. So this is the formula, log x, log mod x. In fact, there is a translation also involved here. So this will be equal to 1 upon 2 pi. That was the constant coming. Integral of omega, Laplacian of u of y, log mod x minus y dy plus 1 upon 2 pi integral over the boundary u of y del upon del n, this n cap, the unit normal of log mod x minus y minus log mod x minus y into del u upon del n cap at y, and integration with respect to the boundary, that is ds. Okay, surface measure. Okay, so this is the representation formula. You can see clearly this comes from the right hand side of the Green's identity, and in the left hand side whatever we have pushed this side. Okay, the derivation of this in the 3 dimensions is demonstrated in the notes, in the handwritten notes. Okay, so this is what I am saying. The solution, the solution of a u can be represented. What is the exact statement? What is the hypothesis of this thing? Just omega is a bounded domain in R2, and n cap is the outward unit normal, is the boundary of omega, and n cap outward u normal vector, and u is any function in C2 of omega bar. Then for any point in the domain, omega is any point. For any point x, you can write the representation formula ux is equal to, given by the formula, in terms of the fundamental solution. This is what is the formula. Any u can be represented like this. So if you see here, all that we have done is to develop and know the fundamental solutions, this thing. Okay. So the same thing we will repeat for the heat equation also. Heat equation, what is the fundamental solution and what is the representation formula. So here the idea was, see here, log mod x minus y. This is also a fundamental solution, because just it is a translation by a fixed point x. X is fixed, and a translation in, because Laplacian is translation invariant. This works because Laplace operator, Laplace is translation invariant. That means if you just translate by a constant, then whatever Laplace equation is, it will be same. Okay, and here in heat equation, it is heat operator is scaling invariant. The base for the entire developing the fundamental solution and representation formula is scaling invariant. Okay, the details why this is scaling invariant, everything is given, and finally what will be the representation formula in the heat case is we get yeah. And what is the fundamental solution? First of all, fundamental solution is the similarity solution. Similarity solution. As I said before, here there are two variables. T is time variable, and x is a space variable, So grouping of of the independent variables x and t gives us similarity solutions. So what should be the grouping that we have to find out? The grouping will be x upon root t, okay, in one dimension heat equation. That is, if you take u, a u of x upon root t will satisfy heat equation. Not only this, there should be something here also. That is 1 upon root t or 1 upon 4 pi root t, u x upon root t will be the fundamental solution. So the derivation is given. And also we have done the maximum principles. Okay, so now come to the solution of yeah. So finally the representation formula in so finally the representation formula here is uxt is equal to um, is equal to 1 upon 2 pi integral minus infinity to infinity, and also we have integral minus infinity to infinity exponential I times x minus y xi minus xi square t d xi. This is with respect to xi, and what is remaining is with respect to y. G of y dy. Okay. This is in one dimension. N is equal to one dimension. This is the representation formula. And what is if you do the integration of this, if you do the integration of this, that will come out to be, that is called heat kernel xy t is equal to 1 upon square root of 4 pi t exponential minus of x minus y whole square upon. Okay, so here this is the fundamental solution. This is the fundamental. See, it is coming in terms of the exponential. Okay. Even this square root of 4 pi t put together. Okay. This is the fundamental solution. And this k is called heat kernel. Because in integral equations, we will always have, so finally x t is equal to 1 upon 2 pi, or if you, 1 upon 2 pi is absorbed. So integral of minus infinity to infinity k of x comma y comma t and g of y t. Why? What is g? What is g? Given a heat equation ut uxx, x is between minus infinity infinity and t is positive variable, and u at the initial condition is g of x. When the heat problem is given the heat problem like this, heat problem is initial value problem, heat problem, initial value problem. Okay. So when we are given the initial value, this g is coming here. Okay. Because this is given to us, this is known quantity. This is known quantity. So u is represented in terms of the integral equation. Integral equation will always have a kernel. This is the kernel. It's called heat kernel, and we have a g of y, which is known here. So this is the integral equation. So every time it is whatever the representation we are doing, it is in terms of the fundamental solutions, and the goal is to find the fundamental solutions. Okay. So how did we obtain this part? That is the main thing. Okay. And even how did we obtain this formula? Okay. This is using the Fourier transforms. How did we obtain is Fourier transforms. You know what is a Fourier transform? Defined by any xi is equal to 1 upon square root 2 pi integral minus infinity infinity f of x or f of y, f of x social minus dx. This is the definition of Fourier transform. Definition of Fourier transform of the Fourier transform of a function of f in L1 or L2. What is L2? Square integral square dx is finite. Function f is square integral function. So for any f which is a square integrable, we can define this f cap, that is Fourier transform, at any point xi. Xi is also in R. At any point xi is integral d fx exponential uh, minus. So inverse Fourier transform. Using these two things, inverse Fourier transform is something like, already Fourier transform is there, f cap is there, f cap is there. For that, we are doing an inverse Fourier transform. at the point x is minus infinity infinity. Already f cap at xi is there. So now it is will be plus I x xi, not x. X is not a vector here in this case. It is scalar only. So xi x d xi. Okay. So also we have a factor here 1 upon square root. This is f check. F check. So using these two things, we can obtain what is the representation formula for the heat equation. So we are given this problem and f and what is the derivative of a Fourier transform? D by d xi of a Fourier transform function g cap at xi. What is the derivative? So do the differentiation with respect to xi of this x minus I xi x dx 1 by square root. So when you I can take the integral inside because these are well defined function integrable functions. So this is equal to this upon 1 upon 2 integral f is independent of xi. The derivative will fall upon this function. What is the derivative of my exponential minus I xi x with respect to this minus I x will come here and exponential minus I xi x dx. So this is sorry, it is yeah, correct, ix. Okay, so this is again the Fourier transform of the function minus I xi f. Fourier transform. Okay, actually Fourier transform of f ix f Fourier transform at side. What is the k number of times? Why we are doing this? Quickly, okay. If we do k number of times, that many factors will I x to the g cap at xi. Okay, minus ix. Okay. So why we are doing this is we need we need to find the Laplacian. So we need at least k is for k is equal to 2. Um, we need the derivative of Fourier transform. Okay. Now another thing is what is the Fourier transform of the derivative? Next, we differentiated here. We different derivative of Fourier transform. What is the Fourier transform of the derivative? What is the Fourier transform of derivative? Suppose I have a function g prime, at x. What is the Fourier transform of this? So write the formula, that is equal to at xi 1 upon square root 2 pi minus infinity to infinity g prime of x exponential minus I xi x dx. So g prime. So you can this integration. Okay, now you can bring the now apply integration by parts. Apply integration by parts formula. Okay. So we have keep g prime as it is and or integrate it exponential minus I xi x between the x minus integral g of x into derivative of this with respect to x now. This will be minus I xi exponential I xi x dx. So this g is a nice function that it vanishes, a compact supported function we take, so that at end extreme points this value is 0. So this is equal to a minus sign is there. So I xi times Fourier transform of xi. So when you take the Fourier transform of derivative, we get a factor multiplied by the Fourier transform. Okay, these two things are needed for us to do the uh, Fourier transform derivatives. Again, now if we have k factors, that is g kth derivative of a function x. If you want the Fourier transform of this at psi will be equal to minus minus that many factors each time this minus will be there, so minus will not come. I xi to the power of k g cap. So now come to the actual solve the problem. Now solve the initial value problem ut minus uxx is equal to 0 is equal. Solve the problem. How to take Fourier transform for the first function? This is PDE. This is the initial condition. Take the Fourier transform of PDE. So that will be you have a function ux del upon del t uxt. Now what is the Fourier transform of this? With respect to x, we will multiply x integral minus infinity. And also you have the other side. If you send this side, you have del square sorry, you have u yeah, correct, del square u upon del x square at x t. So you are taking a Fourier transform, so multiply by exponential minus I xi x integral minus infinity to infinity dx. So I took the Fourier transform both sides. So this so this is and derivative pulled out, and we have what is transform of Fourier transform at xi and t, okay, is equal to here we have like Fourier transform of derivative, two derivatives. So what is that Fourier transform of derivative? We'll get a factor minus I I psi square double derivative. So we have this thing into Fourier transform psi. So this is equal to I square is minus 1, so minus psi square u cap psi. So now this is like for fixed t. No, for fixed, not fixed z, for fixed xi. Xi is always a fixed thing because of we are taking a Fourier transform. So this is like a if you ignore what is xi, because this is like a differential equation. Yeah, that like an ordinary differential equation. Ordinary differential equation f prime or some uh, p prime. P prime is equal to minus psi square. Okay. What is the solution of this? This is multiply by exponential whatever that thing, and in this thing. So we have v of xi is equal to what will be exponential xi square minus xi square t with a constant. Okay. This is the uh, so same thing here. What will happen here? We get, yeah, this is what we get. We get u psi t is equal to a constant times exponential minus xi square t. Okay. Now take the now also take the Fourier transform of the initial condition, that is g cap at psi. So put t is equal to 0 in the above. So we get the constant c is equal to, we get constant c is equal to g cap at psi. So now u cap psi t is equal to g cap psi into exponential psi square t. Now take the inverse Fourier transform. Inverse Fourier transform, both sides. So inverse Fourier transform is multiply by exponential I x xi, integrate with respect to x, minus infinity infinity is equal to integral minus infinity infinity g cap xi exponential minus xi square t exponential I xi I x xi dx. So left hand side is it, right hand side is what? Right hand side is you can write this expand the GCAP. Expand the GCAP. So what we get here is exponential. GCAP expansion will give us integral g of y exponential minus I psi y dy. So this and club this and this, so it is I times this is I minus I times x minus y psi minus psi square d psi. This is one part, and gy dy is. So we have clubbed this exponential and this exponential and even this exponential and put together, exponential put together, and written the, sorry, this is dx, sorry, we'll have the correct inverse Fourier transform will have transform will have integral because we so, okay. So this is the, now what is left out, this already we have written, right? Representation of uxt is equal to this one. Now what is left out is find the integral minus infinity exponential plus I time x minus y psi minus xi square t d xi. This is the actual 1 upon 4 pi t exponential minus, and this is the heat. How this has come? This we have to use the Gaussian Gauss function, Gauss function. Use gamma function, not Gauss function. Gamma function. We know what is a gamma of we know it's what is a gamma of a gamma n, gamma alpha. Gamma n, we know something like 0 to infinity. E power minus x something x power something, gamma function. Use gamma function. Write this or this x square or something. Not x square here, but gamma function definition may be like this, x only. But we have to do a change of variable. Do a change of variable here. Write this in terms of a perfect square of something, and this will come out. Okay. So try to solve this, try to prove this. Okay? Prove that this integral is equal to this. So we'll stop here. So this completes now the heat and this thing. What is left now is Green's functions. Green's functions. Last topic is Green's function. That is also, these are also representation formulas. In the case of Laplace. In the case of Laplace. So that is mainly when it is, what will be the Green's function when it is half space. That is upper half half space in Rn, sphere in Rn. What are representation formulas? So this topic is left. We'll complete this in one class. So after that, we'll have the tutorial sheets discussion. After that, we'll have the exam. Okay. So tutorial sheets also are there. And after completing this, we'll have minor test. Okay. Is that fine? We'll stop here.
Okay, sir.